In this lecture, we'll discuss about design and verification of memory, that also ROM memory, read-only memory. It is a one port memory and we are doing front door access, nothing but we access or read the data through ports, and we are doing without task. Okay, I am not using any task in the test bench. Okay, so this is one port because there is only one address and one read port. If I have two addresses and two read ports, then it will become two port. Okay, so this is the design code. First we'll see the design code. So I started with module and it will end with end module. My module name is ROM and these are the port list. First we'll see the diagram. So this is my ROM memory. I am giving clock and I am giving reset, enable and address. These all are input ports. These are inward to the memory. This port is output port. Here I am reading the data. It's outward. Okay. You know, this clock is for timing. With respect to clock edges, this circuit will work. Okay, that read data will happen. And this reset is to bring the circuit to non-state. Okay, and this is the enable. So when I want to read the data, whether this memory is ready to give the data or not, I can know from this. Okay, I can use active high or active low enable. Here I am using active high, so there is no bubble here. So in active high, if this enable equal to 1, so this memory is ready to give the data. If enable equal to 0, this is not ready to give the data. That's the indication. Okay, and this address, so when I want to read the data, there can be so many locations in this locations or addresses in this memory. From which location or which address I want to get the data, read the data, that address I have to tell now. So for this, okay, and I am going to design a 64-bit ROM. If you understand this code, you can do any bit, any size, any memory capacity ROM. Okay, let us take this is my memory. There are total 16 locations. This is the first location and this is the last or 16th location. Okay, in each location it contains 4 bits. The number of bits in each location indicates width of the memory. This width is nothing but data bus width. So this is the data bus width. Okay, so each location contain address. That address I named in decimal. So 0 to 15, total 0 to 15 means 16 addresses. Okay, so if I represent this address in binary, it will become 4-bit address, because how many addresses? 16. If I do 2 power something, when I will get 16, if the something equal to 4, 2 power 4. So for 16 addresses I need a 4-bit address. Okay, so to represent 16 addresses, each address I can represent, each decimal address I can represent in 4-bit. Okay, so this is a 4-bit address in binary. Okay, so total I will get 16 addresses or locations. Number of addresses, number of locations same, and this number of locations is also called depth of the memory. Okay, so this depth is telling by array and this width is telling by vector. Okay, so in this lecture we can see about vector and array also. Okay, so if in each location 4 bits and there are total 16 locations, then 4 into 16 number of bits in each location and number of locations, it will become 64-bit ROM. Okay, and here we do, in this memory we do only reading, we don't do writing. That's the meaning of read only memory. Okay, now we'll go to the coding. So these are my ports: clock, reset, enable, address, out data. There is no write port because we don't write here. Okay, that we have to observe. So this is the declaration of input ports. These three: clock, reset, enable are scalars, and this address is vector here. Because I taken 16-bit 16 addresses, so I need multiple bits to represent each address. So that's why this address became vector. Okay, and it's a 4-bit size. Okay, this is also input port, and my data also is multi-bit data. So this out data port also become vector. It is also 4-bit size. This size is telling by number of bits in each location. This size is telling by number of bits in each address. Okay, right. And this out data is the output port. Okay. So in the procedural blocks, see here I used this out data in the expression left hand side. So this out data become the reg data type variable. So this is the variable, this is the data type of this variable, and this is the memory size representation. So total how many locations? 16 locations. So this memory of this size indicating array. In the array, variable name comes before the square bracket. So this memory of this size is array. It indicates in depth. Total locations 16, nothing but 0 to 15. And this size, then a memory. This memory variable common to both this bracket and this bracket. So this size, then memory. This indicating vector. This vector is telling width, number of bits in each location, 4 bits. That's why this is 0 to 3. And this memory variable in this procedural block I wrote left side of the expression. So this memory variable also become reg data type. Okay. Now I am writing in behavior style. So I used always procedural block to code the functionality, and I want to make the circuit as synchronous reset. So that's why I have not included reset, and this circuit working with positive edge clock. That's I mentioned. Okay, so for this always procedural block, this is the begin and this is the end. Okay, in this design code itself I am using two procedural block. One is always to code the functionality, and there is another procedural block that is not always, that is initial. I told in previous lectures we can use initial also in the design code. In previous lectures I have shown dollar monitor display related in the design code. There I used initial block. Now this is the second example. I am using initial block. For what I am using here initial block? Because this is the memory. If I want to read the data, there should be some existed data, na? So I only have to keep some existed data. For that data, fixing the data, okay, I am using this initial block in the design code. Okay, so like this also we can use initial block in the design code. Okay, so here I cannot write the data through write port because it is ROM. I can only read. If I want to read, there should be some existed data, na? That data only I am only creating with this initial procedural block. For that I used. Okay, and this always procedural block is to code the functionality. Okay, so this is the begin of this always, and this is the end. Main begin, main end. Okay, so in this functionality of this procedural block, what I have to code? Two things. What happen if I reset this memory? What happen if I release reset? Okay, so here I want to use the active high reset. So that's why if reset, when I do reset, it means reset equal to 1, the out data will be 0. So memory will be 0, it will become 0. So it means I am using active high reset. So before the statement I used begin, and after the statement I used end. Okay, right. Next, else. This else applicable to this reset. Okay, else means if reset becomes 0, automatically it will become 0. Okay, what will happen? Access will happen. Which access? Read access will happen. I already kept some data. So this procedural block and this procedural block both will execute same time. Okay, you may think this block is later. So here only I am fixing the data. Then how I can get data here? Because they execute both at a time, both blocks. Okay, right. So by the time you reading this data already available. That's the reason. Okay. So now in the else case, again I have to use another else in this case. Why I have to use? Because there is a enable. I have to tell what happen if I make enable as 0 and what happen if I make enable as 1. For that reason I have to use else. This else is applicable to this enable. This else is applicable to this reset. Okay. So I am using active high enable. So initially I will keep that to enable as 1. Okay. So again after else I start begin. So this is one block in this always main begin end. This is one part of the code and this is another part of the code. Okay, this part is completed. Now for this part I kept begin and end for this part. This part is started after else na. So from here to here I kept begin end. Okay, right. So for this begin this is the end. For this begin this is the end. For this begin this is the end. Okay, like you can see the indentation also. Okay, right. Straight to this begin, this end came. Okay, so if I keep enable equal to 1, read access should happen. Okay, this is the meaning of enable equal to 1. It is indicating active high enable. Okay, so how read access happen? Memory of address. It means memory of address 0. It means whatever the data in this address, that I have to get at the output port. Okay, whatever the address, this address I give from test bench, then whatever the data in this address, that I have to get in the output. Okay, so before this statement I used begin, after this statement I used begin and end. Okay, this is the begin, this is the end. Now this is the else part. If I make enable 0, automatically it will become 0. What should happen? Okay, write access should not happen. Okay, so in this case I am keeping my address as xxx 4x, because here only I will get all addresses. Here I don't know what is the other address, so I just simply kept all are x. Okay, so that is the out data, and before this statement I kept begin and I kept end after the statement. Okay, so it means when enable equal to 0, read data and address both will become x. So when we run this code, when enable equal to 0 na, we will get address also, data also x. Okay, right. Now functionality completed. Now I have to fix some data. That's why I am using initial block. So for this initial, this is the begin and this is the end, and this is the end module. Okay, so here total how many addresses? 16 addresses. And what is the variable I take in memory? So memory of address 0, memory of address 1, like that. And here in each address I am keeping some 4-bit data. This data you can keep in the decimal format or a binary format, 4-bit binary format. Okay, why I am keeping 4-bit binary? Because in each location I am keeping 4-bit data. That's the reason. Okay, and here why I kept all 111? You can keep any data. For example, I kept these datas. Any data you can keep. That's your wish. Any 4-bit data. Between 0 to 15, any 4-bit data you can keep. See here I given this 4-bit data in the form of decimal. We can give with any base. Okay, right. So this is the design code. Now we'll go to the test bench code. Okay, so here I included my file name. ROM is my file name and module name also. And this is the module starting, and at the ending it will end with end module. My test bench name is TB. So this you know, this you know, this you know, and this also you know, instantiation. Okay. So here I am using this initial block for input generation, address and enable and so my inputs are address and enable na. So here for input and enable, address and enable generation, I am using this. Okay, I already generated some input data in the design code itself. Okay, and I have to generate some clock. So for this initial block is for clock generation. Okay, I taken my initial clock position as 1 and time period as 10, and I taken as example finishing time is 100. So because I am using clock forever, that's why I used finish. This I kept in another procedural block, and for reset generation also I used another procedural block. Initially I kept 0, so initially I am not resetting, but after 30 time minutes I am resetting again. After from starting to 0 to after 45 again I released reset. Okay, this is our wish. I kept this in separate procedural block. And for display I want to see the transcript result also, so I am using monitor. This also I kept in separate procedural block. Okay, so now we'll see. I already told in previous lectures about this monitor, reset generation, finish, clock generation. Now we'll concentrate on this block. So initially I am making my enable 0. Okay, so enable 0 means what will happen? Read access won't happen. Okay, but after 10 time minutes I am making my enable 1, so read access should happen, and I have to tell the address also, from which address I have to get the data. So when I make enable 1 and when I give address, I will get some data in that address. Whether I am getting the data or not, I have to check. Whatever the data I given in the design code to this address, that data I am getting or not, that I have to check in the result. Okay, again after 10 time minutes I am giving new address, but here I have not changed the enable. It means previous enable only, this enable 1 only retain here. Okay, again after 10 I am changing to another address. Here also I have not changed the enable, still it is 1. Later after 10 time minutes I changed my enable and I give an address. So here enable is 0 means right, even I give address, given address, read access should not happen, that I have to observe. Okay, again after 10 time minutes I changed enable 1 and I given another address. So now read access should happen, I have to get the read data. Again after 10 time minutes I change it to another address, but still this enable is not changed, it will remain as 1. Then after 10 time minutes I given my address as xxs. What should I get? I should get x data also x when I give this. Here also the enable equal to 1. Okay, now we'll run this code and we'll check. I am simulating this code in the model sim tool. This is the run file, you can see. Okay, I will copy the path. You have to click no. So here just to move the cursor here, you will get this up down arrow. You drag it down to see this wave. So click here and zoom it. Now we'll analyze this output. This is very important. So I kept my clock initial position 1. After 5 time units, 5 picosecond, it is inverting. So clock came, however I given, it came like that. And initially my reset is 0. I have not applied reset, yet to 30 picosecond I applied reset. Again here I released reset at 45. Okay, this is also happening as I given. Initially I have not enabled. This enable I kept 0. After 10 only I changed it to 1. You can see the test bench code. Okay, so it means from here to here read access will happen. Again from here to here read access should not happen. From here again read access should happen. So here to here even I give from here to here. So from this time 40 to 50 even I give address, I should not get to read data. Okay, because enable is 0. When enable is 0, memory is not ready to give the data. We won't get the data. Okay, and this is the address. So when I made enable 1, that time only I can read the data. So that time only I am giving my address. Okay, so I am giving address, so that time only I can get data. So before it is like a X. Okay, right. So here I enable at a 10, and what address I given here? 1010. Okay, we'll go to test bench. So after 10 time, it's initially 0. After 10 times I made enable 1 and I given address 1010. So 1010 means address, what is the decimal value? 10. In the design code, in the address 10, what data I kept? This is the address 10. 1010 means address 10. What is the data? 0010. We should get to 0010 in the output. See, 0010 came. So I enable and I give an address and I am getting data. Whatever the data is there existed in this address, that data only coming now. Okay. Then again I give another address at this time. So in this address, what is the data? 4 ones. We'll check. This decimal value of this address is 6. In the 6, what we given? 4 ones. See, where is the 6? 6. 4 ones. Okay. Right, it is reading perfectly. Now we'll see what happen if we. So now here I made this enable as 0, but I am giving address. I should not get data, so there is no data here. See, when I disabled, I am not getting data. Again I made enable and I given some address, I am getting the data. Again here I given new data, I am getting the given new address, I am getting the data. Okay, so this is the address, this is the data. This address you have to see in the test bench, or you can see in the RTL code also. So with respect to this address, I am getting this data or not, that you have to check. One thing. Okay, you have to check address and data, and you have to check another thing also. When I make enable 1, that time reading happening or not. When I made enable 0, that time reading stopped or not. That also you have to observe both. Okay. So anywhere we have given same address 1010. So this is all zeros, 1000. Okay, we have not given same address anywhere. Okay, all are different addresses. Okay, so I hope you understood. So the purpose of this project is whether this memory reading properly or not. Whatever the address existed, whatever the data existed in particular address, when I give that address, in that address data is coming or reading out or not, that we have to check. So we did the design code and we verified it, and it is working properly. So design and verification of 64-bit ROM, one port ROM without task and through ports front door access is completed. because here we taken the data through ports only, not hierarchy. If I take from hierarchy, that will become backdoor access. Okay, so design and verification of ROM project completed. In some other lectures I will do with backdoor access, and I will do with two port ROM, or I will do with the task. So we can do this project in different other ways also. This is the basic model, and in this basic model you can change the size, like that also you can again do. Okay, right.